Hi, I'm Shruti Ranganatha Desigan, currently pursuing Masters in Electrical Engineering, specializing in digital system at University of Texas at Dallas. Heard about Trivium Ciphers? Well, now this video describes a hardware implementation of a synchronous stream cipher called Trivium Cipher. What does Trivium Cipher do? Basically, it generates up to 264 bits of key stream from an 80-bit secret key and 80-bit initial value. It consists of two phases, initialization phase and feedback phase. In initialization phase, internal state of the cipher is initialized using key and the initial value. In feedback phase, where the key stream generation is an iterative process which extracts value of 15 specific state bits and uses them both to update 3 bits of the state to compute 1 bit of key stream. This loop takes place until 264 bits of key is generated. Huge, isn't it? Well, now how can we implement this using day-to-day components in the life of an electrical engineer? I have designed Trivium Cipher taking minimum area as my optimization metric. Let's take a look at my schematic. This is a schematic view of Trivium Cipher, which consists of 3 nonlinear feedback shift registers that has 93 flip-flops, 84 flip-flops and 111 flip-flops respectively. Here, this is my C register. This is my C register, which consists of 111 shift register. This is my B register, which consists of 84 shift register, and this is my A register, which consists of 93 shift register. I have made use of true single phase clock D flip-flop configuration. Why is it I have used it? Because of two main reasons. One is to reduce the area because it has very minimum area of 15.549 micrometer square, and the second one is to eliminate any overlapping and non-overlapping clocks which happens in the case of master and slave configuration. And this is the 2x1 mux I have used, and this is my XOR gate I have used, and this is my AND gate which I have used in my Trivium Cipher. Now let's have a look at my layout. This is my optimized layout of Trivium Cipher, which has an overall length of 70.3 micrometer and height of 89.65 micrometer, which comes to overall area of 6302.395 micrometer square, power of 18.80 nanowatts, average propagation delay of 0.6389 nanosecond, and consumes an energy of 26.35 nanowatt. I have minimized my area by stacking 17 flip-flops per row in order to achieve the ideal aspect ratio, which is 1 in a square form. My ideal aspect ratio is 0.784. Here in every alternative row, I have flipped the flip-flops in such a way that 2 rows have a common supply or a common ground. I have done this in order to reduce my area and the distance between two RX, that is 0.6 micrometer. And I have used until metal 3 in order to implement my design. This is my C shift register, which consists of 111 flip-flop. This is my B shift register, which consists of 84 flip-flop, and this is my A shift register, which consists of 93 flip-flop. Initially, I approached the design by using a square supply and ground rail, but I found that when I'm doing that, as the distance increases, the substrate contact resistance decreases, and therefore I have to increase the substrate and contact in every flip-flop at one point of time. So in order to avoid that, I stack my flip-flop in such a way that I reduce my overall area. Let's have a look at the output waveform. Now, my project mate Padmavati is going to explain about the output waveform. Thank you.
Hello everyone, I am Padmavati. I am currently pursuing my Electrical Engineering Masters in University of Texas at Dallas. I am here to present the latter part of the Trivium Cipher project, which is nothing but the simulated waveforms. In this, once the layout and the schematic is matched, the netlist is generated using the QRC tool. Once the netlist is generated, the SPICE code is written for simulating the output waveform. Once the spice code is written and it is compiled, the output waveform is loaded. In this, we have the select line for the multiplexer, the clock signal for the D flip-flop, that is the shift register used in this project, then the reset signal, and the secret key. The secret key is considered to be the output for this project. The secret key is generated based on the key and the initial value loaded to the shift register, and then the secret key varies based on the reset signal as well. If the reset is high, the secret key is generated based on the feedback of the shift registers. Thank you for watching this video.